Hello everyone, in this recording we'll discuss frequency framing. One of the very basic ideas in statistics is that no matter what data you've collected, things could have turned out differently. You might have had a different group of participants in your sample. Whatever experiment you conducted might have had different sources of measurement noise. No matter what measurements you finally get, the results could have been different. And yet, whenever we do visualization, we usually just show the raw data. Right? We don't often think about how can we communicate the fact that there are different hypothetical data sets that we could have very reasonably gotten if it had just been a different day, a different experiment. So these next few lectures are about this question of how can we communicate uncertainty in our visualization? And one of the first things to ask is, how can we communicate probability? So you might be familiar with just showing probabilities in this sort of bar chart, right? So what I've done here is I've sampled from a few different coin flipping kind of mechanisms. So the first one, you have probability 0.01 of turning up heads. Next one, 0.1, last one's 0.4. I've just made a bar chart of the empirical probability under these coin flipping mechanism, right? So the one that's very rare, you have very few of the coins actually coming up heads. Then the next one you have about the kind of empirical probability looks a lot like the real probability. So this is the kind of the standard way to show it. But then it turns out that this is not a very good way as far as human perception goes. Right? We are just not very good at translating these heights of bars into actual frequency intuition. It turns out that we are much better at comparing frequencies if we are able to see them in this kind of form, where you associate each of the outcomes with its own graphical mark. And so here I'm basically showing just each of the coin flips as a little square, and I'm coloring the square by whether it was heads or tails. Here's the 0.01, the very rare one. Here's the 0.4, the more common one. And now people tend to be much better at judging uncertainty and judging frequency calculations when you see it in this way up front. And we can make difference comparisons much better. Right? So whenever showing kind of these sort of raw probabilities, it's much better to show it in this kind of frequency framing strategy than to simply show a bar chart. Right? It might be standard, but it's definitely not the optimal way to do it. Okay, now that works great if you have categorical outcomes, right? Like heads or tails. What happens if you have continuous outcomes? So you can imagine something like party A is in an election against party B. There's a certain percentage by which party A might win or lose. Right? You can think of it as some sort of distribution. There's a certain mean of the difference. There's a certain uncertainty about it too. Right? You could just plot it like this sort of distribution. But it turns out that just like in the bar chart example, this is not the optimal way to show it. You can run kind of human subjects experiments and ask people to communicate what they perceive. And this way of showing it turns out to be better. Right? So instead of showing just the density, you kind of imagine hypothetical outcomes at different points along this difference curve. It looks a lot like the density, but just by breaking it into hypothetical outcomes, we can perceive the difference much better. Okay. So how am I making this plot? I'm using the ggdist package. So the first one, this is a stat slab, and this one is called stat dots. Everything else is just to kind of clean up the theme, right? But whenever you want to make this sort of continuous variable broken into these discrete hypothetical outcomes, you can use this stat dot command. Okay. So that's if you had just one outcome. You can actually do this for multiple at once. Right, so what this example is, we are going to try to look at chocolate bar ratings across many countries. So this data set has for many, many countries. Here I've just filtered down to some subsets. And I'm showing two ways of showing. So the first one is stat dots, just like what we had before. And the next one is stats dots interval. And the question that this is answering is, if you went into a grocery store, picked a random chocolate bar from one of these countries, what is the rating that you would expect? Like, how good is that chocolate bar, right? You could just show a histogram, you could just show a density, but that is, again, is not as evocative as if you have the frequency framing where you show each kind of potential outcome, or you show the distribution of outcomes. The difference between these two is one is just stat dots, so only the dots. The other one has an interval below it. So it helps orient, where is the center, about how much does it extend. Okay. A interesting variation is called a ridgeline thought. So here you can use stats lab. It's kind of drawing these densities, but then they kind of line up in this way, and it looks like they're stacked on top of each other. Right? So this is useful when you have many, many kinds of outcomes, right? So here's an example, right? If I had many more countries, you can still read the ridgeline plot relatively easily. But if I had the dots here, they start overlapping with one another, right? The only way to get around this is to make the dots really small, and that also isn't legible, right? So you lose a little bit because you no longer have the frequency framing seeing the specific kinds of outcomes. But if it's illegible, it's still better to show at least the densities than just intervals.